like this. A two-stroke cycle CA engine delivers a brake power of 368 kilowatts, while 73.6 kilowatts is used to overcome the frictional losses. It consumes 180 kg per hour of fuel at an air fuel ratio of 20:1. The heating value of the fuel is 42,000 kilojoule per kg. Calculate number 1. Indicated power. Number 2. Mechanical efficiency. Number 3. Air consumption. Number 4. Indicated thermal efficiency. Number 5. Brake thermal efficiency. Solution to this problem can be given as: it is a two-stroke diesel engine and brake power is given as 368 kilowatts. Therefore, indicated power is given as brake power plus frictional power, which comes to 368 plus 73.6, which is equal to 441.6 kilowatts. This is the indicated power of the engine. Hence, mechanical efficiency could be calculated as BP by IP, that is 368 divided by 441.6, which comes to 83.3%, which is very much in the range of the expected value. Usually the mechanical efficiency of an IC engine will vary between 75 to 85%, which I had already mentioned earlier. Now coming to the second, that is air consumption rate. Air fuel ratio into mass consumption rate of the fuel, that gives the air consumption rate, that is amount of air consumed by the engine per minute. Air fuel ratio is given as 20 into mass flow rate of the fuel. Mass consumption rate of the fuel is 180 divided by 3600. It comes to 1 kg per second. indicated thermal efficiency is equal to indicated power divided by mass consumption rate of the fuel into calorific value. Numerator, if it is in kilowatts, mass flow rate should be in kg per second. Indicated power which we got it as 441.6 kilowatts divided by 180 by 3600 into 42,000 kilojoule per kg. That comes to 21% of indicated thermal efficiency. Brake thermal efficiency is equal to indicated thermal efficiency into mechanical efficiency, which comes to 0.21, that is indicated thermal efficiency into 0.833. It comes to 0.175 or 17.5% of brake thermal efficiency. Now I shall do a problem on the 4-stroke petrol engine. A 4-stroke petrol engine delivers a brake power of 36.8 kilowatts with a mechanical efficiency of 80%. The air-fuel ratio is 15:1 and the fuel consumption is 0.4068 kg per kilowatt hour. The heating value, which is also known as the calorific value of the fuel, is 42,000 kilojoule per kg. Calculate number 1 AP, that is indicated power. Number 2 frictional power. Number 3 brake thermal efficiency. Number 4 indicated thermal efficiency. Number 5 total fuel consumption. Number 6 air consumption per second. The solution to this problem could be given as, because BP is given and mechanical efficiency is also given, immediately we could calculate the indicated power, that is brake power divided by mechanical efficiency, that is 36.8 divided by 0.8, which comes to 46 kilowatts. Frictional power FP is equal to IP minus BP, that is 46 minus 36.8, 9.2 kilowatts. Brake thermal efficiency is equal to brake power divided by mass consumption rate of the fuel into lower calorific value, that is BSFC is equal to 0.4068 divided by 3600. It yields 1.13 into 10 power minus 4 kg per second. Kilowatt second. Therefore, brake thermal efficiency is equal to 1 by 1.3 into 10 power minus 4 into 42,000. That yields 21%. There is important formula that could be used many a times here, is that because 1 BSFC or BSFC is the mass of fuel required in kg to produce 1 kilowatt hour of brake work. Therefore, brake thermal efficiency is equal to 1 kilowatt hour is equal to 3600 kilojoules. That much brake work is produced. 3600 divided by BSFC into calorific value. Whereas calorific value should be in kilojoule per kg and BSFC should be in kg per kilowatt hour. So this is the formula what I had used above. That means since CV is constant for a fuel, brake thermal efficiency is inversely proportional to the brake specific fuel consumption. This is one of the conclusions we could draw from the definitions of BSFC. Now coming to the problem, indicated thermal efficiency is equal to brake thermal efficiency divided by mechanical efficiency into 100. That comes to 26.25% of indicated thermal efficiency. Fuel consumption rate could be calculated as BSFC in a kg per kilowatt second into brake power, that is in kilowatts. So the resultant answer will be kg per second, which is given as 1.13 into 10 power minus 4 into 36 point. It comes to 0.0042 kg per second of fuel is consumed by the engine. Air consumption in kg per second could be calculated as mass consumption rate of the fuel into air fuel ratio, which comes to 0.0042 into 15, that is 0.063 kg per second. This is the air consumption rate by the engine. Now I shall define volumetric efficiency of IC engine. Let me draw the figure of the internal combustion engine. This is the stroke volume. There is two extreme positions of the piston. This is clearance volume. The entire stroke volume, which is pi by 4 d square L, where d is the bore dia and L is the stroke length. The entire stroke volume, that is pi by 4 d square L of the engine, cannot be used to draw the air in the case of diesel engine or air fuel mixture in the case of petrol engine during the suction stroke, because there are certain inherent losses, which means the actual volume of the air or air fuel mixture that is sucked into the cylinder during suction stroke will be definitely lesser than pi by 4 d square L. The reasons for this loss of volume or decrease of volume is: number one, throttling at the inlet valve. There is a pressure drop across the inlet valve during suction due to the throttling effect, and because of the inside exhaust gases, leftover exhaust gases are hotter, they will also contribute to the decrease in volume of the air or air fuel mixture that is inhaled or sucked into the cylinder during suction stroke. So volumetric efficiency is defined as actual volume of air or air fuel mixture that is sucked into the cylinder during suction stroke divided by swept volume or stroke volume of the engine. So definition I would like to give like this: the volumetric efficiency of IC engine is defined as the ratio between actual volume of air in the case of CA engine or air fuel mixture or air petrol mixture in the case of SI engine, that is sucked into cylinder during suction stroke and the swept volume or stroke volume of engine, that is pi by 4 d square L. Therefore, volumetric efficiency is the ratio between actual volume of air or air fuel mixture in the case of petrol engine sucked during suction stroke divided by pi by 4 d square L. In fact, volumetric efficiency of an engine depends on so many factors. In fact, it could be given either on the mass basis also, that is mass of charge actually inducted divided by mass of charge represented by swept volume at ambient pressure and temperature. Either way, it could be given either on the mass basis or on the volume basis. Usually the volumetric efficiency given on the mass basis we will follow in future problems. Now let's do a problem given in GATE 1996 on IC engines. A 4-cylinder 4-stroke SI engine has a compression ratio of 8 and bore of 100 mm with stroke equals to bore. The volumetric efficiency of each cylinder is equal to 75%. The engine operates at a speed of 4800 rpm with an air-fuel ratio of 15. Given that the calorific value of fuel is equal to 42 megajoule per kg, atmospheric air density is equal to 1.12 kg per meter cube, mean effective pressure in the cylinder is equal to 10 bar, and mechanical efficiency of the engine is equal to 80%. Determine the indicated thermal efficiency and the brake power. The solution to this problem could be given like this. First of all, let us calculate what is stroke volume of engine, that is pi by 4 d square into L, pi by 4 into 100 by 1000, that is bore dia, because stroke is equal to bore into 100 by 1000, that gives the stroke volume in meter cube, or which is also called as the swept volume of the engine. Now we would calculate the mass of air fuel mixture that would fill entire stroke volume at atmospheric conditions is equal to V stroke into density of air fuel mixture. Assuming density of air fuel mixture as density of air, atmospheric air, we get mass of air fuel mixture that would fill entire stroke volume is equal to V stroke, which is already calculated as pi by 4 d square L, into 1.12, that is the atmospheric air density, which is assumed as density of air fuel mixture. So we got the kg of air fuel mixture corresponding to the V stroke. Since air fuel ratio is given as 15, which means 15 kg of air mixes with 1 kg of fuel to give 16 kg of air fuel mixture. Hence 16 kg of air fuel mixture has 1 kg of fuel. Then V stroke into density of air fuel mixture, that is the mass of air fuel mixture that would fill the entire stroke volume, has how much fuel, that is equal to pi by 4 d square L, which is calculated earlier, into 1.12 divided by 16. This is kg of fuel per each cycle. Since it is 4-stroke cycle engine, there are n by 2 number of cycles per minute if n is RPM of the engine. Hence, mass of fuel consumed per minute is equal to pi by 4 d square L into 1.12 divided by 16. This is the mass of fuel consumed per cycle into n by 2. This is equal to pi by 4 d square L into 1.12 by 16 into RPM is given as 4800 divided by 2, so many kg per minute. If we divide with 60, we will get within a kg per second, that is pi by 4 into 100 by 1000 whole square into 100 by 1000 that is L into 1.12 divided by 16 into 2 divided by 60, so many kg per second. This is the mass consumption rate of fuel, m dot F. It is given mean effective pressure as 10 bar. Given it is. Therefore, indicated power of the engine can be calculated as PM LAN by 2 by 60 into K, where K is the number of cylinders. K is given as 4 cylinders. Therefore, indicated power is equal to 10 bar into 100, that is so many kilopascals. While calculating indicated power, please convert mean effective pressure into the kilopascals into what is bore dia? Pi by 4 into 100 by 1000 whole square into stroke length, that is 100 by 1000 into 4800 divided by 2 by 60 into number of cylinders, that is 4. This directly gives the indicated power in kilowatts. Therefore, indicated thermal efficiency is equal to indicated power in kilowatts divided by mass consumption rate of the fuel in kg per second into calorific value of fuel in kilojoule per kg. Now, having calculated indicated thermal efficiency, we can calculate brake power of engine is equal to indicated power into mechanical efficiency. That is how we can obtain the brake power also. Now I shall solve a problem given in GATE 1998. It is a problem on turbocharged engine, which is given like this. A turbocharged 6-cylinder diesel engine has the following performance details. Number 1, work done during compression and expansion is 820 kilowatts. Number 2, work done during intake and exhaust, that is equal to 50 kilowatts. Number 3, rubbing friction in the engine, that is equal to 150 kilowatts. Number 4, net work done by turbine, that is equal to 40 kilowatts. If the brake mean effective pressure is 0.6 megapascal, determine the bore and stroke of the engine taking the ratio of bore to stroke as 1 and engine speed as 1000 rpm. First of all, let me draw the figure how a turbocharged diesel engine look like. Turbocharging means there is a centrifugal blower which is taking atmospheric air, and that blower or centrifugal compressor will be increasing the pressure of the air. This compressor is driven by the turbine. This turbine, what drives the turbine? The exhaust gases leaving the engine, whereas the centrifugal blower supplies the air at high pressure into the cylinder. The gases, exhaust gases leaving the IC engine are driving the gas turbine. The turbine in turn drives the centrifugal compressor or centrifugal blower, and the turbine produces some power which may be given to the crankshaft of the engine, because after driving the compressor, the turbine network done may be supplied to the crankshaft for taking external load. The air at high density is supplied into the cylinder at a higher density than the atmospheric air. Atmospheric air enters the compressor where it is pressurized, and then this air goes into the cylinder at higher density than the atmospheric air, and air is compressed, and we have the fuel injector that is ignites which will supply the diesel fuel into the combustion chamber, and the diesel is ignited because of the high temperature air, and the gases are formed doing work, and in the exhaust gases leaving the cylinder drives the gas turbine, and the turbine drives the centrifugal compressor. This is the actual setup of the turbocharged diesel engine. Turbine drives the compressor. Turbine in turn is driven by the exhaust gases leaving the engine cylinder. In fact, the gases leaving the cylinder are at a higher pressure than the atmospheric pressure. Then only they can drive the turbine because of the pressure difference of the gases between the turbine and the atmospheric air. In this problem, the work done during compression and expansion, that network is positive plus 820 kilowatts, whereas work done during intake and exhaust, that is negative loop, that is minus 50 kilowatts, and rubbing friction, that is minus 150 kilowatts, and the net work done by turbine after driving the compressor, in fact, that is 40 kilowatts, which is supposed to be positive because that is output. This is 40 kilowatts work is given by the turbine to the crankshaft. So adding up all these powers, we get the net brake power output. Hence, net brake power output of engine is equal to plus 820 minus 50 minus 150 plus 40. So many kilowatts. Therefore, net brake power output of engine is equal to 760 kilowatts. It is given that brake mean effective pressure of the engine is 0.6 megapascal, which is equal to 0.6 into 1000 kilopascals, that is 600 kPa. Now, from the brake power formula, that is 760 kilowatts is equal to brake mean effective pressure into LA, that is stroke volume, into N by 2, because it is a 4-stroke diesel engine. All the turbocharged engines are 4-stroke engines, into K divided by 60, where LA is the stroke volume. That is 760 kilowatts is equal to 600 into L is D, because L by D ratio is 1, 5 by 4 D square divided by 60 into N. RPM is given as 1000 by 2 and 6 cylinders, from which we can get the bore dia in meters, which is equal to stroke length of the engine. Hence the problem. Now let me do a problem given in GATE 1999. The problem is given like this. A large diesel engine runs on 4-stroke cycle at 2000 RPM. The engine has a displacement of 25 liters and a brake mean effective pressure of 0.6 meganewton per meter square. It consumes 0.018 kg per second of fuel. Calorific value is equal to 42,000 kilojoule per kg. Then determine the brake power and the brake thermal efficiency. Now the solution to this problem could be given as: the given engine is 4-stroke cycle engine, 4-stroke engine, CA engine, diesel engine, and V stroke, or that is 5 by 4 D square L, which is known as displacement volume, is 25 liters, that is 25 into 10 power minus 3 meter cube. BMEP is given as 0.6 megapascals, that is 0.6 into 10 cube kilopascals. Fuel consumption rate is given as 0.018 kg per second of fuel. Because brake mean effective pressure engine is of the engine is given, brake power output of the engine is brake mean effective pressure into LA, that is stroke volume, into N by 2 by 60. Because it's a 4-stroke engine, I had written N by 2 and into 1, where only one cylinder is there. Single cylinder diesel engine. This is equal to 600 kilopascal, that is brake mean effective pressure. Stroke volume is 25 into 10 power minus 3 meter cube. RPM is given as 2000 by 2 divided by 60 into 1. This gives the brake power output directly in kilowatts. Then coming to the brake thermal efficiency, which is defined as brake power output in kilowatts divided by mass consumption rate of the fuel into calorific value, BP in kilowatts, which is already calculated earlier, divided by mass consumption rate of the fuel is 0.018. Calorific value of the fuel is given as 42,000 kilojoule per kg. This gives the brake thermal efficiency. It is around 20 to 25%. That is the usual range of brake thermal efficiencies of CI engines. Now let us solve a problem given in GATE 1995. It's a matching problem. List 1 is given as heat engines. List 2 is given as the respective corresponding cycles. A in the list 1 is gas turbine, B petrol engine, which is also known as spark ignition engine, C Stirling engine, D diesel engine. Number 1, right side list 2, constant volume heat addition and constant volume heat rejection. Number 2, constant pressure heat addition and constant volume heat rejection. Number 3, constant pressure heat addition and constant pressure heat rejection. Number 4, heat addition at constant volume followed by heat addition at constant temperature. Number 5. Heat rejection at constant volume followed by heat rejection at constant temperature. Looking at the gas turbine cycle, which is a Breton cycle. Gas turbine runs on Breton cycle. Breton cycle has got two constant pressures and two isoentropic processes. Two constant processes and two isoentropic processes is gas turbine. For gas turbine, this is the cycle. On PV plane, two isoentropics and two isobars. Heat addition at constant pressure and heat rejection at constant pressure. That is, A is for answer is A for 3. So looking at the petrol engine, which is running on the Otto cycle, heat addition at constant volume and heat rejection is also at constant volume. That is B for 1. That's the answer. See, Stirling engine. If you look at the Stirling engine, the Stirling cycle is two isotherms and two constant volumes. This is constant volume heat supply and constant temperature heat supply, and constant volume heat rejection and constant temperature heat rejection. So for Stirling engine, the answer is heat addition at constant volume followed by heat addition at constant temperature. For C, the answer is 4. Looking at the diesel engine last, or diesel cycle, heat addition at constant pressure and heat rejection at constant volume. So constant pressure heat addition and constant volume heat rejection. So that is D is answer is 2. So A for 3, B for 1, C for 4 and D for 2. That is the answer for this question. Now I shall solve an objective question given in GATE 2003. The question is asked like this: a diesel engine is usually more efficient than a spark ignition engine because A. Diesel being a heavier hydrocarbon releases more heat per kg than gasoline. B. The air standard efficiency of diesel cycle is higher than the Otto cycle at a fixed compression ratio. C. The compression ratio of a diesel engine is higher than that of an SI engine. D. Self-ignition temperature of diesel is higher than that of gasoline. The answer to this question is diesel engines, CI engines are thermally more efficient than petrol engines, because diesel engines employ, the answer could be given as the diesel engines employ far greater compression ratio R than petrol engines. R of CI engines is in the range of 16 to 22, whereas R of SI engines is only limited to 6 to 10. So the diesel engines are employing far greater compression ratio than the petrol engines. Hence, thermal efficiencies of CI engines are thermally more than that of SI engines. That is the correct answer. Now I shall solve a problem that is given in GATE 2007. The stroke and bore of a 4-stroke spark ignition engine are 250 mm and 200 mm respectively. The clearance volume is 0.001 meter cube. If the specific heat ratio gamma is equal to 1.4, the air standard cycle efficiency of the engine is 46.4%, 56.1%, 58.2%, D 62.8%. The solution to this could be given as, here L is given as 250 by 1000 meters. Bore dia is 200 by 1000 meters. Immediately we can calculate stroke volume, that is pi by 4 d square L. The compression ratio R is Vc plus Vs by Vc, that is 1 plus Vs by Vc, that is 1 plus pi by 4 d square L by Vc. Clearance volume is also given. This is a 4-stroke cycle engine, spark ignition engine. Therefore, the Otto cycle is the standard cycle for SI engines. We can calculate it as 1 minus 1 by R to the power of gamma minus 1.